Okay, so today we're doing more stuff. This is Physics 1A for May 10th. And today we're going to continue talking about the relationship between torque and angular acceleration. We're going to talk about objects that roll without slipping. This will be like things like the tires of your car, your bicycle, objects that are rolling down ramps. And then with what time we have left, we're going to kind of introduce and talk about angular momentum. And that's the plan for today. So at the end of class last time, we discussed this equation, which talks about that if I have a bunch of torques acting on a system, that if I sum up all of the torques acting, that it's going to be equal to the moment of inertia of the system multiplied by the angular acceleration. Basically giving the idea that torque produces angular acceleration. And we want to look at this problem right here, which I gave you all some time to look at before we started. So it says a rigid rod, and there's the mass and the length, has a small block of mass 100 grams attached at one end, so that's attached down here. The other end is attached to a frictionless pivot that allows the rod to rotate in a vertical circle, so the rod can basically rotate around like this. The rod starts at rest when it's horizontal. The first thing it says is to find the moment of inertia about the pivot, and then we want to find the initial angular acceleration, and then some other things. So we'll do these two first, and then we'll get into solving for the rest of these. This is a pretty extensive problem that actually covers quite a few of the topics that we have talked about for the last couple weeks, so it's a good way to get started this week. All right, so let's start with part A. We want to find the moment of inertia about the pivot. How can we do that? Any ideas? Okay, so that's the equation that we discussed last time for moment of inertia. Don't know that we'll need to use that equation in this case. We have basically like a long rod, and then we have an object kind of attached to the end. So when you have multiple objects like this, and you know what the moment of inertia of the individual objects is, you can find the total moment of inertia of the whole system by basically adding the moments of inertia for the two different objects. So we just need to basically think of it as a moment of inertia for the rod plus the moment of inertia for that ball that's at the end. The problem says a block, but we'll just call it a ball. Moment of inertia is a scalar, so we can add it together like this. What should I use for the moment of inertia of this long rod right here? Yeah, what can I use for this piece right here? The moment of inertia for the rod. 1 over 12 mr squared. Okay. Or 1 over 12 mr. It should be r squared, right? So that's the moment of inertia for... There's basically two different moment of inertia equations for rods, right? There's one moment of inertia equation for a rod that's rotating about its center. And there's another moment of inertia equation for a rod that is rotating about the end. See, what are these? And which, how do you know the difference between the two of them? One of them is 1 over 3 and one of them is 1 over 12. So which one's smaller? Both of them are multiplied by m times the length squared, right? So which one of these has the 1/3? And which one has the 1/12? The top one's smaller, and 1 over 12 is smaller, right? So this is 1 over 12, and this is 1 over 3. If you don't know where these are coming from, there's a table in your textbook. Yeah. Okay, so which one do we use in this problem? This one, right? Because this rod's rotating about the end, so we're going to use the moment of inertia for our rod is going to be 1 over 3 m times L squared. Plus, we have to include the moment of inertia of the ball as well. How can I figure out the moment of inertia for the ball? Yeah, you just use m times r squared. So when you have like, I guess I can write this over here. If I have like let's say a pivot point and then a string and then I have a ball, and let's say that ball has a mass of m and its radius is r, the moment of inertia for this is just m times r squared. So let's use, so 100 grams is the mass of the ball. Let's call that capital M, I guess. So we'll say capital M is going to be equal to 100 grams is 0.1 kilograms. And that way we can put it into this equation. So we do plus, for the ball we're going to have what I'm calling capital M multiplied by the length from the pivot to where the ball is. So that's L squared. And there we go. And we can just calculate this, right? Does anyone have any questions? Okay, so this is going to be 1 over 3 multiplied by little m is 0.36. And then L is 1 meter. Plus big M is 0.1 kilograms. And the length is 1 meter again. So it looks like we're going to get, is that right? 0.22 kilogram meter squared. Okay. So just to kind of review, when you have an object that is composed of multiple objects, the total moment of inertia is just the sum of the moment of inertia of the parts. So you can always break it up into parts that you already know the moment of inertia of and then add them together to get the total moment of inertia. Okay. Continuing right along. This is where the problem starts to get pretty tricky. That first part's definitely very easy to do, especially once you know how to do it. Part B says to find the initial angular acceleration. So we're trying to find, I'm just going to call this alpha initial. And what this means is to find the angular acceleration of the system when it's released. So let's go back and see what was going on. We have a pivot point right here. The system starts from rest, and it's free to rotate, which means when we release this from rest, it's going to swing down like this. And what we want to figure out is what the angular acceleration is, which we can find by figuring out something about torque. So the angular acceleration when it's in this position right here, that's what we're going to call alpha initial. So to do this, what do we need? What do you all think? What should we do to kind of figure this out? How should I get started? Find the torque. Torque equal to L times mg. Assuming that T is for torque. Yeah, I mean, we need to do some stuff with torque, okay? All right, so then in order to do that, what should I do, though? Yeah, free body diagram, exactly. So let's draw a diagram of what's going on here. We'll use some of the shapes. This is our rod, and we'll just put a ball at the end. It doesn't need to be perfect. So again, this thing has a mass of big M. The rod is going to have a mass of little m, and this is our pivot point right over here. That's our pivot point. So we're going to sum up all the torques acting here, which means we need to identify what all the forces are. I need to move this down a little bit, actually. So what are the forces? 2W. Do you mean 2 weights? Is that what you're saying? By 2W? There's the weight due to this one over here. So we can, let's just put in all these vector arrows first. So we're going to have a weight over here, right? So that one's just going to be m times g. The weight of the rod has weight. It's a rigid rod. We're going to assume that it's a uniform rod, which means that its center of mass of the rod is going to be right in the center. So we'll come here to what looks to be the center right here, and we'll draw a vector for the weight of the rod, which is quite a bit bigger, so we'll just make it a little bit longer here. Try to make that straight. Okay, so this one's going to be 3mg, or not 3mg, sorry. It's called little mg. Okay, what other forces are there? X and Y components of the pivot point. Yeah, so there's going to be some forces over here by the pivot. And my guess is that just based on the way that the system is set up now, there's only going to be like a Y component of the pivot right here. There's just going to be like an upward force. Like this. And it really needs to be a lot bigger. Maybe I should just make these other two smaller. They don't need to be so big. That way, things can kind of balance out a little better. It doesn't have to be equal, so this is fine, I think. I'm just going to call this one, I don't know, we could call it P for the pivot force. We could call it N because it's kind of like a normal force, effectively. Let's just use P. This is basically going to be the force that the pivot places on the rod. Okay, so we're calling that one P. Okay, and now we just need to basically apply this equation right here and solve for the angular acceleration. So let's do that. We're going to be summing all of our torques about the pivot point, basically. So writing that equation down, sum of the torques is equal to I times alpha. The angular acceleration direction is this way. And I'm going to call that alpha initial. So we'll put that area in this equation too. So both mg and big mg over here are going to create torques that cause the angular acceleration in that same direction. So we can make all these torques positive. The pivot isn't going to create any torque about this point because the pivot force pulls on this, but this is something that's going to be, we're going to need to calculate that later. Okay, so net torque is equal to I times alpha. The torques we have are going to be mg right here. And I need to multiply by the lever arm, which is going to be the distance from here to here, so that's L over 2. So we have mg times L over 2. Plus, we have big mg, and it's a distance of total distance of L from the end. So we multiply this times L, and then that's equal to I times alpha. We already calculated the moment of inertia right here, so I'll just write here I times I of the pivot, and this is multiplied by alpha sub I, which we're solving for. So we can easily solve for alpha initial here. Let's plug all the numbers in. Okay, so little mg, m was 0.36. What I'll do here is this is divided by 2 plus big M is 1.1 kilograms. And both of these have G times L in them, so I'm going to pull that out to the outside. And then L is 1 meter. And we need to divide all of this by I pivot, which is right there. And that's going to be our initial angular acceleration. What do you get if you calculate that? 0.8018. Really? Is that what you get? You want us to get the same thing? There's no way to keep this in full screen mode and use the calculators there. That's too bad. We'll just do like this then. Okay, so we're doing okay, so that times 9.8 divided by 0.22. Yeah, I got 12.47. Yeah, that sounds better. Okay, so this answer is 12.5, we'll say. Okay, now, what do I write down for my units for this? If you look at the units in here, what do you get? Like, if you just look at the units from, kilograms times meters per second squared times meters divided by kilogram meter squared, what unit do I get out of that? Yeah, 1 over second squared. So basically, we just end up getting pretty much inverse second squared here, right? That's what's left over. Kilogram, kilogram cancel. Meter times meter cancels. We're just left with 1 over second squared. Okay. But what did we say that the unit for the angular acceleration was that we normally use? What unit do we normally use for this? Yeah, radians. It's not radian, it's radians. Radians per second squared. Radians per second squared. So the radian unit, it's never going to show up. You have to just kind of put it in by hand. Because it's not... It's kind of like a dimensionless unit because it comes from a ratio of lengths, right? You think about the way that we define radians. The way that radians are defined are... You take a circle... and you look at an arc length of that circle and you call it S, and you say that the angle that subtends that arc length is theta, and the radius is R, then the angle theta is defined by taking the ratio of S over R, right? which means this gives you radians, but S is measured in meters and R is measured in meters. So radians doesn't really have like a dimension, you know? That's why you can kind of just put it in these type of equations. Okay, so that's our initial angular acceleration. Anyone have any questions? So part C says find omega. Omega is the angular speed or angular velocity of the rod when it's vertical. So the rod's going to swing down from here to here. We'll draw a new picture. And we want to find the angular speed of the rod at that time. So what this is going to look like at that time is our rod is going to be vertical. Our pivot is still up here at the top. And what else to write? Oh, we still have the ball at the end. And the idea is that if it's released from rest, when it gets down to here, it's going to have some angular speed that we're going to call omega, and that's what we want to calculate. I'm going to call it omega final, because that's just normally how we label these things, okay? All right, so how do we want to solve this? What's the best way to go about finding this angular speed? Yeah, energy. We can use energy. Why do we have to use energy, by the way? Why do you say we have to use energy? As opposed to doing what? Why do we have to use energy? Why can't we use something else? Because we're rotating in a circular direction. That's not really the reason why. Why do we use energy here instead of... What's another option? What would be another option? Yeah, kinematics would be another option. Why can't we use that? Why can't we use, like, the equations that we derived the other day? Like the circular motion equations. Where do they show up? Right here? No, it's the day before. Or the day before that. I don't know which day we covered them. Okay, you're saying because we don't have constant acceleration. Okay, why is the acceleration not constant? That's right, that is the reason why. Why is the acceleration not constant in this case? And why did we call this the initial angular acceleration before? Kinetic energy of the rod. That's not really the answer, no. This rod starts off and it has all this torque acting on it, right? What happens to those torques as the rod starts to rotate down? Do they get bigger? Do they get smaller? Do they stay the same? Yeah, they get smaller, right? Because the angle between the weight, for example, and the lever arm here starts off at 90 degrees. And as the rod rotates, that angle gets bigger, which means that the sign gets smaller. So the angular acceleration changes because the torque on the rod gets smaller and smaller until when it gets here, what's the torque on the rod in this position? Is there any torque on the rod? All the forces acting on it act down now, right? So you can't really have any torque anymore, right? Okay. So yeah, the angular acceleration starts off to be this big, but actually when it gets down to here, there is no angular acceleration, at least for a moment, until it starts to decelerate as it swings up past this point. So when you have non-constant angular acceleration, to go back to what Kelvin was saying, that means you have to use energy. You have no other choice. You're required to. So I just wanted to kind of make sure everyone understood that when he said we have to use energy, you actually have to. There is no other way to do it. There is another way to do it, but it involves using calculus and would definitely be a lot harder. So this is the easiest way for sure. Okay, so that means that if I want to use energy, then I'm probably going to have to draw another picture on here, but that equation is this equation. Work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. In this case, it's just going to be the change in potential energy due to gravity. And to use this equation, we basically just need to kind of identify the 2 points that the object rotated from. So I think there's enough room that I can write this up here. So this is going to be our initial position up here, where we're going to say that we need to pick some like y coordinates, right? So I'll let you all decide how we want to do this. But I'm going to say here that its initial angular speed in this position is 0. Whoops, not question mark, but is 0. And the next thing we want to do is talk about the change in height that's going on in this problem. Now there's 2 different ways to do this. Normally we would just need to write down, okay, what is the initial position and what is the final position down here? But it's a little bit more complicated in this case because we kind of have 2 objects basically. We have a rod and we have a ball, and each one of them undergoes kind of like a different change in height, right? For example, the initial y coordinate of the ball right here, suppose that we call that 0. Let's say that we make this point right here to be y equal to 0. Okay, and we make, positive up, so this is our y coordinates now. That's the y direction, is going to be positive y up. So if I call the initial coordinate of the ball to be 0, what would the final y coordinate of the ball be? If the pivot is at 0, yeah, y final for the ball then would be negative L. Does everyone agree? Because again, this is our positive y direction, and we're calling this y equal to 0. Okay, so y final for the ball is negative L, y initial for the ball is 0, okay? We also need to do the same thing for the rod now. For the rod, what would y initial for the rod be? Well, it's also 0, right? But then y final for the rod, so the rod swings down to here. What do I want to use for y final for the rod? What point on the rod should I use to talk about this? I don't think this has really come up in this class before. It's going to be L over 2, and why is that? Why did you all choose negative L over 2? The center of mass, exactly. Okay, so the center of mass of the rod is right here. And when it swings down, the center of mass of the rod is right here, right? So when we talk about delta y for the change in potential energy, if I have an object that's not just a point mass, like this, then you need to use the center of mass of the rod. Okay? You always need to use the center of mass in that case. Okay, so we've got the information that we need. We know enough pieces of information here where the only unknown is going to be omega final, so we just need to kind of shovel everything into our equation here. So let's do that. So we have work done by non-conservative forces. I'm going to write this equation out starting right here. So 0 is going to be the work done by non-conservative forces. For change in kinetic energy, there's really two terms, okay, right? There's going to be 1/2 I times omega final squared minus omega initial squared. And this is going to be the moment of inertia of the pivot. I'll just write I sub p right here that we calculated in the first part. That's going to be for this piece. Now you can also write down a translation equation too, because kinetic energy is also like 1/2 mv squared, right? But this object is undergoing pure rotation in this case. Pure rotation. There is a fixed pivot. That pivot is not moving. All of the objects that are in the system, which are the rod and the ball, they're all undergoing pure rotation. They're not translating in any way. Does that make sense? So as a result, here I'm going to put in here plus 1/2. I don't want to make this equation too long, but I guess you'd have to put like the mass of the rod, which is m, multiplied by the velocity of the center of mass of the rod. Look at all these. There's gonna be a lot of subscripts here. I'm gonna end up erasing this. Final squared minus the velocity of the center of mass of the rod initial squared. So you do not need to do it this way though, because in this system it's pure rotation, so we don't need to worry about this stuff, okay? So I'll just write pure rotation, so we can neglect all of this stuff right here. Does that make sense? We're going to look at problems where you have to include that stuff here next, but for now it's pure rotation, so you just need this term. Can everyone get on board with that? Does anyone have any questions about why I'm doing that? For the kinetic energy. Okay. For change of potential energy due to gravity, there's going to be two terms. There's going to be one for the ball. So remember, the ball is capital M and the rod is little m. So for the ball, we're going to have capital M multiplied by, well, G, and then times delta Y, which will be Y final ball minus Y initial ball, plus the mass of our rod is M. That times G times, same thing, YF rod minus Y initial rod. I could also put on here, center of mass, but hopefully that's kind of understood. Okay, so now we just plug in all the information that we have. We are trying to solve for this right here, and all of the initial information was 0. So anywhere we have, like, this is, like, let's go through and mark out all the things that are 0. So that's 0, that's 0. Omega initial is also 0, right? Yeah, that's 0. So we're left with just this, all of these terms. Okay. We want to solve for omega final, so let's move all the other terms to the left-hand side. Hold on a second here. Oh, no, we're good. So these are going to end up being negative numbers, so it's going to work out just fine. Okay, so we're going to have negative, let's keep using red. Okay, so we're going to have negative mg Y final ball. Okay, we'll wait to put that in until the next step. You know what? Let's not do that. It's going to be easier to do all the algebra and stuff once we don't have all these subscripts, so let's just plug everything in. So 0 equals 1/2. We know what I pivot is, but I'll plug the number in later. Times omega final squared plus big MG. Y final ball was negative L. Plus Y final rod is negative L over 2. Okay, and then we just want to solve this. Sorry, this equation kind of got kind of sloppy. Solving this for omega final, we're going to have omega final is going to be equal to 2 over I pivot multiplied by mgl plus mgl over 2 square root. Does that look right to you all? Basically add these two terms to the other side and then multiply by 2 over I to clear this, and then take the square root. Does that look right? Okay. All right, let's plug all the numbers in. So the square root of 2 divided by, I think IP was 0.22. And capital M is 0.1. That was the ball, right? Just checking, because the ball should have gone through a change in height of L, and it did. So this one's 0.1 kilograms times, now both of these terms have a G and an L in it, so I'll just move those to the outside. So 0.1 kilograms plus little m was 0.36 kg divided by 2, and then times G times L, so times 9.8, and then L was 1 meter. I apologize, these equations are really quite sloppy and they kind of ran into this, so sorry about that. I'll probably move this over just a little bit so that they're not so crunched up here. So there's our equation, and if we come back over here, okay, so let me know what you all get on this one. Five. You get the same answer. I'm pretty sure that's the right answer. Kind of reminds me of what I've gotten in the past. So we're going to call it 5. So omega final is 5. Again, radians per second. We have to just kind of like put the radians in, because if you look at these units right here inside of this equation, you're going to be left with probably 1 over second squared, because you have meters times meters, cancels out with meters squared there. You have a kilogram in these two that cancels out there, so you just have 1 over second squared. You square root that, you get 1 over second, but you have to throw the radian in yourself, because you just have to remember that omega is measured in radians, basically. Okay, anyone have any questions? Okay, that's just part C. We still have 2 more parts to do. The next question is to find the force at the pivot when the rod is vertical. This problem is really good because it kind of covers a lot of topics all at the same time. Okay, so find the force at the pivot when the rod is vertical. So let's come down to our picture right here for when the rod is vertical. Let's copy that down to here. Now we're on, this is part D, right? Let's get a different color for this too. Let's go back to full screen. So this is part D. Now we can go ahead and redraw the same forces that we had before. The only difference is they're going to have a different orientation now, right? So coming onto this picture here, we're still going to have a force coming from the center right here, which is the force, the weight of the rod. So we label that one m times g and draw it right there because it's coming from the center of mass. We're also going to have a force coming from the end, which is from the ball, which is going to be big mg. And there's a force at the pivot as well, which we called P before, so we'll call it P again, which is going to point up like this. And that's our pivot force. And we're trying to calculate what this is equal to. So, what do you all think? How should we go about doing that? How should we find the force at the pivot? Sum all the torques. So in this case, there is no torque though. There's forces, though. There are forces, that's true. We can do forces. Okay, so we called this the y direction before, right? Positive y. So you're saying we should sum all the forces in the y direction, and that should be equal to the... what are we going to write over here? Something like the mass of the whole system. Multiplied by what? What are we going to multiply this by? Mass of the entire system times alpha. We can't really do that because the units won't work out. Because if I do m times radians per second squared, I don't get force. So we can't just multiply by alpha. We can't do that. You want to add a centripetal force in here? Centripetal force is going to definitely be part of this, but we're not going to add a pseudo force into our equation. You think it's not g? That's not what we're going to write right here. What do you all think? What should we write down? R omega squared. What R are we going to use? Definitely on the right track. So what I'm going to say is that what we need to multiply by here, when I have a system of objects and I want to understand something about how they're operating, what we can do is we can multiply by the acceleration of the center of mass of the whole system. So we can multiply this by the acceleration of the center of mass of the system. So not that center of mass, but now the center of mass of the whole system, basically. I didn't mean to do that. I just wanted to get rid of the little x right there. Okay. That's what we need to do. Now, how is this accelerating? Some of you have already kind of said it, but in what way is this object accelerating? No. I mean, gravity is what, like, kind of has it moving, but it's not the force of gravity that's really, like... Sorry, let me ask the question a different way, I guess. How would you describe the acceleration of this object? What direction does it point in, and how would you describe it, I guess, is what I'm trying to say. Let's start with the easy part. What direction is the acceleration? It's not down. Yeah, it's up. Why is it up, Rena? Because it's rotating in a circular path, exactly. Anytime you have an object that's rotating in a circle, it's always going to have an acceleration towards the center, right? Augeron. What does that mean? Radial. You mean a radial, yes. Yes. Yes, that's what it is. That's right. It's radial acceleration, exactly. Okay, so we know it has a type of radial acceleration. We also know, somebody said, I think it was Andrew that said this, that we can define that radial acceleration by taking this expression, right? R omega squared. But this R, when we've used it in the past, it always was some type of a... It was really obvious what the R was. In this case, we need to use the distance to the center of mass. Okay? So we need to figure out where that is now. We need to find out where the center of mass of our rod plus ball is, okay? So that's the first thing we're going to do. We're going to find the center of mass of the system. I can't remember if we talked about this in this class. I don't think we actually have done any center mass calculations at all. But maybe you've done some of them on your homeworks, and maybe you've read about them before. So the way you do this when you have two objects like this is you find the center of mass of one of them, which is, we know, right at the center for the rod. And you use that as the position of the object. And to find, like, in this case, what we're going to locate is the y-coordinate of the center of mass. And to find this, all you have to do is to take the mass of each object that you have in your system, m sub I, multiplied by the y-coordinate of the object. You sum over all of those, and then you divide by the sum over the total masses of the system, basically. This is how we find the center of mass of this object. So let's do that. So we have two different objects here. We're going to use like y1 and y2 for this just to keep it simple. So one object is the rod, and its center of mass, which I'm going to call y sub 1, is equal to, let's use the same coordinate system just to be consistent. So if we call this y equal to 0, then the y-coordinate of the center of mass of the rod is going to be at negative L over 2, right? And the y-coordinate for the other object, which is the mass at the end, which we'll call y2, is going to be at a y-coordinate of negative L. And then using this equation right here, what we're going to get is we're going to take the mass of our rod, which was little m, times y1, plus the mass of the ball, which is big M, multiply that by y2, its y-coordinate, and then we're just going to divide by m plus m. And that's going to give us the y-coordinate of the center of mass, which is going to end up being, you know, somewhere down here, basically. So if we calculate what that is, so little m was 0.36 kilograms. Multiplied by its y-coordinate, which is negative L over 2. That's where the center of mass of the rod is. Plus the mass at the end right here, which is 0.1 kilograms. Sorry. And we multiply this by its y-coordinate, y2, which we're calling negative L. And then we divide by m plus m, so by 0.36 kg plus 0.1 kg. Keeping in mind that L is equal to 1 meter, then this is going to be something like this, 0.609. Do you all agree? So we get, and it's negative, we get negative 0.609 meters. That's the y-coordinate of the center of mass, using y equal to 0 to be this point right here. Okay, so that means, I don't know how much I want to draw this on this picture here, but that basically means this distance between here and here is 0.609 meters. That's the distance to the center of mass of the object. And that's what we're going to use in this equation. Okay, does anyone have any questions? Okay, let's throw everything together. So, our equation says we need to sum up the forces in the y direction. We're taking the positive y direction to be up because it's accelerating in that direction. It has centripetal acceleration. The forces that we have are P, which is positive, going up, minus little mg minus big mg is equal to m plus m. We know what those are. We're just going to leave that as m plus m, and we're trying to solve for P. We know that the acceleration of the center of mass is going to be equal to the y-coordinate of the center of mass. I'm just going to take the absolute value of this right here. And that's going to have to be multiplied by omega squared, which we already calculate. So I'm just going to write omega final squared because it's the omega that we calculated right here. And we just need to solve this basically. So we end up getting P is equal to mg plus big mg plus little m plus m times the y-coordinate of the center of mass multiplied by omega final squared. I think m plus m shows up in everything here, so we could actually factor that out to the front. Just factoring m plus m out of everything. So we're going to get oh, and again, I kind of dropped it, but we're using just the absolute value of YCM here, not the negative version. So 0.609 times omega final, which was 5. Squared. This will give you the force of the pivot, and the force of the pivot then is going to be If you all have any questions, can you put them in the chat now while I'm typing this all in? I'm just going to put this exact number in here. Yes, it is. You're right. That is right. This squared should not be here. Yep. Thank you. It's 5 radians per second. Whole squared. Yes. Thanks, Paige. Okay, I got 11.508. You all agree? And the units for this should be newtons, and if we look through the stuff that's happening here, you do get newtons. It is important to note that the same thing happens with radians here in reverse, where if you look at the first term, it's basically just, you know, mass times acceleration, so that gives you force, right? Kilogram meter per second squared is our definition of what a newton is. But if you look at the second term, you get kilogram times meters divided by seconds squared, which is also a newton, but it's multiplied by radians squared. So again, you just basically, you ignore this at this point, because this is basically, this is giving you a unit of newtons times radians squared, right? But again, the radians you just kind of ignore. You don't have to write that down. So if you're like, if it really bothers you to like include and follow all your units and stuff like that, then you have to kind of ignore that when it comes to the radian stuff. Which I think can be kind of tricky, and I know that's kind of confusing, but I don't know what else to say. That's just how it works, because this isn't really a unit; it's just a ratio. So, okay, did that all make sense? We still have one more part to this. We're gonna have to take a break though. I don't think we're gonna be able to finish this. It's a pretty long problem. Did that all make sense? We have this object that's rotating, so it has radial acceleration or centripetal acceleration, whatever you want to call this. And, yeah. Now, I don't know if you can tell, but there actually is another way to do this, where you'll get the exact same answer. Where you can basically say that the sum of all the forces in this case has to be equal to the mass of one object, like the ball, times its radial acceleration, plus the mass of the other object times its radial acceleration. And you'll get the exact same answer. In fact, if you actually plug in what we got for y center of mass right here into our equation, you can kind of see that the m plus m's cancel, and you end up with these two terms. Anyway, so what is the last part? How fast can we do the last part? Oh no, we're done. Oh no, we're not. We just did this part. We have to come back and we have to solve for this part here. So, okay, we'll do that, the initial force at the pivot last. We haven't solved for this pivot force. So that's what we'll do when we come back. So let's take a 10-minute break. We'll start again at 3:15. And if you want to, you can try to solve that last part.